enough, you have given enough effort, you have spent enough time to try to find out, figure out things, how to proceed, etc. Okay. So, all right. So please, others, I'll give until this evening to submit, and then we'll discuss it afterwards. After I'll go through the homework and see what kind of issues people have faced, and I'll try to talk about those things. Okay. All right. So, so a brief recap. Basically, so far, what we have done, we have learned about solving. We have talked about solving algebraic systems, well, linear systems. I did not spend too much time on this, but assume that you already are familiar with this. So linear systems, okay. Then nonlinear systems, basically set of nonlinear algebraic equations. And then we started talking about ODEs. And each case saw actually some examples, some of the actual real life physical problems. So physical examples over here, okay, and then over here, okay, and then ODE we had broadly two kinds of problems. Okay, initial value problem, boundary value problem. Initial value problem, we looked at methods which were forward Euler, backward Euler, trapezoidal, and the methods. Okay, and which is actually one of the kind of predictor factor. This is what we have. Okay, this class of problems. So we'll look at second order and fourth order both. Okay, and then boundary value problem. Here we look at, of course, the finite difference based approach, right? Okay, here I had two kinds of methods. One was based on approximating the derivatives. Okay, the second was shooting. Okay, and then other was the second approach was basically approximating the solution in terms of basis functions. And we look particularly with a choice of basis functions being cubic splines. Okay. Cubic splines. But you have to keep in mind that that's just one set of basis functions. You can decompose your solution or write your solution in that form, and then analyze, and then basically substitute in differential equation and try to match the boundary condition and the coefficients. Okay, so that is the basic procedure still remains the same. Only your choice of basis functions may change. Right? So I think we have discussed so far, and yeah, of course we had a proper, and then there was a problem that we discussed, which was, I mean, we have discussed other problems also, but this problem was useful in the sense that it's PFR with axial dispersion. Okay. The good thing about this problem is that it combines many different techniques. Okay, so many techniques are utilized. Meaning about describe methods which are like, for example, Newton's method, then solving the initial value problem, then of course yeah, so and then of course you can, well, depends on level of then of course you have mixed boundary conditions, which makes it difficult to handle. Okay, you don't have a shear norm and kind of boundary condition, you have a mixed boundary condition at another boundary. So these are the issues which make this problem interesting. Okay, basically mixed boundary condition is what makes it interesting, and the ideas which are used are basically we use this method. This idea is utilized and initial value problem solving is utilized. Okay, so this is you can I'll encourage you to do the same problem by different methods. So, like for example, you can try doing it using finite difference rate approaches. One of you have already done using this. You can try using this and also using this. Okay, I mean approximating the solution in terms of cubic spines. So I'll strongly encourage you to try them out. Okay, this is if you have this way, and then you can compare the efficiency of each method. You can see which one gives you more accurate results and so on. Okay, all right. So next topic is actually, well, this broad topic is PDEs. But before I start PDEs, there's one very important topic which is relevant for PDEs is something that we're going to start and probably right now is PDE. Okay, so now let me ask you this. How many of you are familiar with Fourier series and Fourier transforms? Have you seen it anywhere? You must have seen it in one of the maths courses, probably. Fourier series and Fourier transforms. Signal processing? Well, are you doing signal processing course? Well, it is related to signal processing, but is it like part of the BTech curriculum? Okay, so you have seen but do not remember. That's fine. I'll just quickly browse over it. Okay, it's good to know that you have actually met this topic. Okay, so why do you mention signal transform? Well, like example. Sure. Yeah, it is used in signal processing. So, but first time it was basically proposed by Joseph Fourier. Can anyone tell me what context was it proposed? You know when to deal with what kind of problems was this idea proposed by? Yeah, it involves periodic functions or something. Exactly. That's correct. That's correct. We'll talk more about. I'm just asking. My question is heat transfer, right? Absolutely, absolutely. Heat transfer. Well, yeah, heat transfer exactly. So it is about conduction. To be more precise, it's a conduction. So heat or basically heat equation. So heat transfer involves all different kinds of equations, right? So conduction and convection and radiation will have different kind of governing equations. Right? So this is about when we're looking at the conduction equation, which is also the same as diffusion equation. Okay? And that is one of the very important topics in this course, so on how to solve it, etc. So basically the simplest heat equation or diffusion equation that can be written as second derivative is proportional to first derivative. So it's a partial differential equation, it's a PDE. Okay? And we'll talk more about that in more detail. So, but it's basically second derivative of a function is proportional in space. It's proportional to first derivative in time. Okay. So, first derivative in time. If you have this kind of equation, or we should appear on the other side. Okay, so this is the kind of diffusion equation. So this is really that when we were trying to came up with this idea, and we'll talk about that in detail later. But anyway, so we'll come back to this equation. Correct? What I'm going to talk about today is that I just want to give you the brief account of how it was, how it came into place, right? So Fourier series and transforms. Now it's so basic idea is something that we have already discussed, which is any function can be decomposed into set of basis functions. Okay, so that is the basic idea. Any function can be, well, I'm writing it very loosely, and probably if I'm saying this to a mathematician, he would strongly object. So, well, this any is within quotes because some properties have to be satisfied, but we assume being engineers or not non-mathematicians we'll assume that all such properties which need to be satisfied by the function are satisfied. Okay? So I'm not going to give details of differentiability, continuity, etc. Okay? So suppose I have a function which is sufficiently smooth, etc., and then can be written as a linear superposition of. We have already seen this in context with solving the boundary value problem using cubic expansion. There we constructed the kind of basis functions that we constructed with cubic splines, which were like finite ranged functions centered, looking like a bell, and it was a finite range. It was zero elsewhere. Within a range, it was not zero, and it has a particular shape. And this was constructed using stitching by stitching different cubic functions in different regions, okay? Joining them. So those were the our basis functions. So now basis functions, as I told, this entire idea is basically motivated by or basically inspired by the observation in vectors. Okay, in three-dimensional vectors, any vector could be written as x dx plus y dy plus z. It's like a projection vector, right? So you can choose these to be your basis vectors, okay, and these will be your weights of relative weights of these different these will be numbers, okay, x, y, z, and that will be basically how much weight do you assign to this basis vector, how much weight do you assign this vector, and so on, and therefore this R can be written as basically a set of numbers. Okay, so R can also be represented as x, y, z. Okay, and these would be basically the coefficients associated with basis vectors, right? So in the same manner, functions also can be written. So you can any function f of x can be written sum of basis function by kx. Right? So these are the basis functions. Right? These are analogous to these vectors, basis vectors, and these AKs are analogous to these coefficients x, y, z, etc. These like coordinates of x in this in reference to these particular basis sets. Okay. All right. So what is the condition? Ex, Ey are basis or x, no, Ex, Ey are the basis. X, Y, certainly. Ex, Ey are the basis functions. These are basically these are the reference. So the basis functions are reference vectors. Basis vectors are reference vectors, and x, y, z are my numbers along by which I go along those particular directions to reach a particular point. Okay? X, y, z are numbers which are analogous to AKs, and Ex, Ey, Z are analogous to IKs. Okay, is that all right? Wait. The next line in parenthesis. You mean to say this line? Is this line you're referring to? Yeah. So sure. This line, this line tells me is that only gives me x. I should have written it like r equal to x. Well, if you assume x1, x2, x3 to be xyz, then xi, ei cap. Okay. And if I have already decided EIs, if I know that is, if I decided what the choice of basis set is, then I can represent R by just specifying these three numbers. That's all. Okay. So that's why I wrote it this way. So you know that vectors are sometimes written by just the three numbers. That's what it means basically. Okay. Follow. So okay. So now the thing is that what is the requirement that the particular class of function serves as basis function? How do you ensure that? You have a set of functions and they serve as basis functions. How do you ensure that? How to ensure that a set of functions may be good for considering them as basis. Can you choose any kind of functions as basis functions? That won't be possible, right? So remember again, this condition is decided based on what we know about what we have learned from the geometry of the three-dimensional space, right? We know that basis functions cannot be expressed in terms of others. I mean, box product is zero. What is box product? Well, triple product. Okay. Well, okay. Yeah, right. Absolutely. So in three dimension, you define triple product. So box product, when you say box product, I will confused. So I think you are referring to triple product, right? Am I right, Amit? You are referring to triple, yeah. So triple product is good for three-dimensional fields, right? But generally speaking, basic idea, well, that is a mathematical relationship which arises from the fact that any vector cannot be represented as a linear sum of the rest of the vectors. Okay, any member of that set cannot be represented as a linear superposition of the rest of the vectors. Okay, so that, for example, Ex cannot be written as any, if you have x and y, Ex, y, and z. Z vector can never be represented whatever way you sum Ey and Z, whichever way superposition way you sum it, you will always give a vector in this plane. You'll never get Ez. Okay, and same holds for any pair. Okay, so that is the idea, and so that additionally you can make. So remember, basis vectors need not be orthogonal. Okay, so you could have probably, for example, in three-dimensional space, not be orthogonal. Okay. For example, in three-dimensional space, you could have chosen this to be your, so you can say E1, E2, and E3 could have been chosen as, but these angles need not be these angles need not be 90 degrees, right? So this is also a good choice of basis function. As long as you cannot write E3 in terms of E1 and E2 or E2 in terms of E1 and E3 and so on, okay, then you are good. Okay, which would mean to say that E2 does not lie or any vector does not lie in the space spanned by the other remaining n-1 vector, or n-dimensional space. To generalize this, when you say that any vector cannot be, so this vector E2, for example, cannot lie in the plane described by E1 and E3, or E1 and E3 cannot lie in the plane described by E1, the other two, pair of the other two vectors, right? So this is also a good choice of basis vector. But what makes life even simpler is to choose such basis vectors which are orthogonal. Okay, so orthogonality makes when you represent a vector in terms of orthogonal vectors, then then basically algebra becomes very simple. Mainly because the dot products of two vectors are zero, so you take components, you don't have to worry about other direction. Okay, so well, we'll not I'm not going to go into the details of that, but simply the treatment becomes easy. Okay, if basis vectors are all orthogonal. Also orthogonal. Okay. So so this is an orthogonality condition is if you take any two pairs, the dot product is 0. Right? Dot product between any pair of vectors is 0. Okay, this is what we know, what we have learned from our understanding about three-dimensional space, right? So same ideas we extend to functions in mathematics. Okay, and except that mathematics you don't have three-dimensional space. You have a multi-dimensional space. You have many points. You can actually decide. Okay, you have, as I told you, dimensionality will be decided by how many discrete points you have to represent the function. Okay, so on. So so how do you define? Then the question comes: if the two vectors you will select as basis vectors or basis functions. If there are two functions, okay, so now functions as basis functions, or you can say orthogonal basis functions. Okay, what would be the condition? The dot product should be 0 if it had been vector. What is the analog of dot product for functions? So you have to find an analog of, need to find an analog of dot product. In context with functions, how do you define dot product, right? Or how do you define, or what kind of quantity would you choose which would be analogous to dot product? Can anyone think of something? Well, so let's look at physically what does dot product mean? You have vector v1 and v2. Okay, physically means it's kind of overlap, okay, or shadow of this guy onto this thing, right? Shadow one vector onto the other vector. So it's a kind of projection, or it's a measure of overlap. Dot product is a measure of overlap. Some kind of qualitative measure of overlap. Geometric projection, that's correct, exactly. So I'm going to interpret it as a measure of overlap and then extend this idea to functions. Okay? So it's a measure of overlap. So when two functions overlap, so if their two functions do not overlap, the dot product would be 0, and the two functions overlap, dot product would be non-zero. So how can you quantify overlap between two functions? Well, it's a very simple. Take the product and integrate it. Overlap is always defined between, let's say, from point A to B. Okay. And this would be a measure of overlap between two functions between 2 points. Okay, so from A to B, that can be considered to be a fairly acceptable analog of dot product between two functions fx and gx. Okay, checking orthogonality using series. Which series? What do you mean by series? So how do you check using series for functions? I do not. I'm going to see if we can talk about that. Okay. So yeah, anyway, so what I'm coming to is that dot product between two functions I'm going to define like this. Okay, so with this definition, I think we are all set to check whether a function is, or a pair of function is orthogonal or not. Okay, so just a second. Hello, 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 hello. Sorry about that. So now I'm going to look at a particular kind of functions which are periodic with period. So these are the functions which are periodic with period 2 pi. Let's call this f of x and satisfy the property which is f of x equal to f of x. Well, acha, Anand, it's simply, I mean, if you have function like this, let's say, and other function like this, okay, I want to see the overlap. So whenever they are, basically, I want to, like if you go along x, this is f of x or g of x, okay, then these are the two plots are given like this, and I want to see how much they overlap in this range, okay. But a simple idea would be just look at if they are perfectly overlapping, let's say, what would it look like? They would be the same, right? They would exactly, so they would go like this, probably, okay. And if they're perfectly non-overlapping, they would probably be like this, okay. So perfectly like a reverse overlapping kind of thing, right? So in this, you can see that whenever this is positive, this is negative. So if you multiply this and add it up, this should turn out to 0. Okay. Well, actually, it will not. I should say, for example. So, for example, if it is not overlapping, then that would mean if it overlaps in some region, it will anti-overlap in other, right? So if the values are the same, having the same trend in one region, then other function will be anti-overlap. So that net overlap is zero. Okay. That is the basic idea. So that is the measure of overlap. I can say that way. Explain why is it analogous to, what is the motivation behind defining this as a measure of overlap. It's simply the fact that if they overlap, the values will be actually swinging together. Okay, they are anti-overlapping. The values will be kind of opposite in sign. Okay, and therefore, if they overlap in one region and not well, anti-overlap, perfectly overlap in one region, and the kind of anti-overlap is a very strange term I'm coining, but anti-overlap in the other region, the net overlap will be 0, right? And so therefore you can choose those product to be, and some of those products of the functions, okay, that will be 0 in this case. Okay? Whereas it will be non-zero in this case. Okay? So when they are perfectly overlapping, it is not 0. When they are overlapping and anti-overlapping, that would be 0. Okay. So therefore, I am going to choose that as my defining property of that as my condition that is analogous to measure of overlap. Is that all right? Am I able to convince you or not? Yeah, right. But remember, it's on the same side of axis. That's right. Overlap means it's the same side of axis. But remember, two functions can be need not be on the same side of axis always, right? So how do you? It's a basically it will be a more like in a statistical property, right? You cannot define by a single value, right? You have to look over a range first of all, and also in the range it may so happen that it may swing together in one part and may not swing together in other part, right? So if that's a kind of variation, and you have to define in terms of like more like in statistical sense, then all you need to do is basically if you can think of something else, you let me know. But I think it appears quite sensible to me that if you define it this way, that's probably the very simplest way of defining overlap between two functions, right? So for example, if there are two functions, let's say one function is like this, okay, and other function is like this. Okay, Anand, let me ask you this. What would be the overlap of these two functions? Let's say this is f1x, which means these could be two cubic or two splines that we've discussed, right? This goes like this, and this function goes like this. What would be the overlap? 0, right? Now if I multiply fx into gx integral, what would it turn out? Fx into dx is 0 in this range because gx is 0 here, and then when gx becomes finite, fx becomes 0. So fx gx integral dx will be 0 in this range. Is that correct? Now suppose you have these two functions. Do you think overlap should be 0 in this case? Then this or this will be not, no, right? But and now if you calculate fx integral gx dx, okay, so for this range you'll get 0 value. In this range you will get non-zero value, and then again you will get 0 value. So if you define your integral from here to here, the net overlap will be non-zero due to overlap only. This integral is not 0 because of overlap only. Okay? This is probably a good example for convince you that this integral is a good measure of overlap. Is that all right? Yes or no? Okay. All right. So I guess even for the rest of the class, I guess this is probably convincing enough for justifying justifying this decision to choose that this can be a good definition or good way to quantify overlap between you for quantifying overlap between two functions. Okay. I think this forms a basis of that choice. Right? Okay. So now let us look at some. So we are going to talk about periodic functions. Okay, with a period 2 pi. Okay, and these can be expressed in terms of basis functions, which may be orthogonal basis functions. So such functions can be represented in terms of basis functions, which are basically sine mx or cos mx. So sine mx, where m is mx. So sine mx, where m and n are integers. Okay, so that is the idea basically. Okay, first of all, why are we going to choose? Why is this a natural choice of basis function? First of all, if f of x is periodic with period 2 pi, then all these functions will be periodic with period 2 pi. Definitely there will be periodicity of 2 pi. Of course, so what is the periodicity of sine mx, by the way? That's periodicity is 2 pi by m. Right? You all know that sine ax or cos ax has periodicity of 2 pi by a. Periodic with period of 2 pi by m. And similarly, cos nx will be periodic with period of 2 pi by m. Okay, that's a fundamental period. So if you plot them with 0 to 2 pi, and m and n are integers, okay, so it can be 0, 1, 2, 3, 4, etc. Let's forget 0 for now. Let's say they are non-zero integers. Then it swings m times or n times between 0 and 2 pi. So for example, if I choose m to be 1, sine function is going to look like simply this. Okay, and cos function is going to look like simply something like this. Okay, we all know that. Okay, and then if I take m to pi, suppose I take 2 pi to be, I take m to be 3, then it's going to swing 3 times. Sine 3x is going to swing 3 times starting from this end. 1, 2, something like this. And similarly, if you take cos 5x, it's going to swing from left end to right end. This would be sine 3x. Okay. This would be sine 3x. And similarly, cosine function is going to swing, let's say cos 5x, going to swing like 5 times. So 1, 2, 3, 4, and 5. Please pardon my poor drawing, but you understand this has to sufficiently thin. I mean, the lambda should be sufficiently small so that it goes 5 times over going from left hand to right hand. Okay, so that is something that you should already know. Okay, so that would mean that in the period of 2 pi, that would imply over 2 pi over x change of 2 pi, these two functions will definitely repeat itself. Okay, sin mx and sin nx or cos nx will definitely repeat itself. Okay, that is ensured. Okay, so that forms the base. So basically, a function is the, so first kind of intuitive justification of these choosing these functions is that they satisfy the periodicity criterion that is basically present with our original function. Okay? This is my original function, and I have chosen these functions which are already periodic with period, which already repeat itself after period 2 pi. Okay, so they can be chosen to represent this function. That's the first thing. And secondly, they're orthogonal. Okay, so let's see. So there are some properties which are relevant here. Some properties, some mathematical properties of these functions, which you can always check. So for example, I know that cos mx and sin nx going from minus pi to pi. Okay, what would be this value equal to? Can anyone tell me? What would be this equal to? Cos mx sin nx dx from minus pi to pi. You don't have to do the integral. You can just look at this and tell me. And just look at this expression and tell me essentially dx. You don't have to actually perform. Yeah, 0, right? Because well, just look at the expression. This is even function. This is odd function, right? Cos is an even function. Sin is an odd function. Product is an odd function. Odd function from minus something to plus some same thing will be 0. Okay, so that value is 0. Okay, that you know. That is one property that is relevant. And this you can see that tells me that any sin nx and cos mx, if I define my dot product to be in overlap integral from minus pi to pi over the period 2 pi, right? If I define my overlap integral or the dot product or the analogous of the dot product to be overlap integral from minus pi to pi, then you see that these functions are orthogonal. Okay, the sine so functions from sine family and cos family, they will be mutually orthogonal for any choice of m or n. Okay, because they will always the net overlap will be 0 if you consider from minus pi to pi to be your uh, range of integration. All right. So that is first property. Other property which would be relevant later. So cos mx dx we already know that would be from minus pi to pi, and that would be the same as sine mx dx minus pi to pi. So over entire period, the function oscillates even number of times, right? So whatever times it does upswing, will go to the negative swing, right? Since this entire period is 2 pi, and in 2 pi it oscillates m times, right? That means m complete oscillations are there, and for one complete oscillation, it is as many times positive as negative, so that the integral will be 0, right? So that is a very simple justification. I don't have to calculate or do the integral explicitly. Okay. All right. Other results. So this would be, let's say, first one. This is the second one. Third one. How about if you choose functions from the same family, cos mx and cos nx here? that would be a little non-trivial. Okay, so that would be turn out to be equal to, let's say when m is equal to n. Okay, and let's say, well, first case, let's say m and n are equal and they are equal to 0. So that's if m or n are 0, m is equal to n equal to 0, then I have 1 1 plus 1 dx, that is 2 pi, simply 2 pi when m is equal to n equal to 0. When equal to m is n and not equal to 0, okay, then what is going to be the value? You can check that, turns out to be 5. Okay, and when m and are not equal, okay, then it turns out to be 0. Okay, so which tells me again that even the cos functions among their own family, they are orthogonal. If you choose m and n to be different, okay, meaning if you use different functions, the cos x and cos 3x, their integral is 0. Okay, so therefore their overlap is 0. So cos mx and cos nx for m not equal to n, they are orthogonal. And similarly holds, same thing holds with cos and sine. Okay, and similarly you can look at the overlap between sine families, or functions from the sine family, sine mx, sine mx dx. What would that be equal to? That is going to be equal to 0 if n is not equal to n, and that will be 5 if n is equal to. Okay, that is from minus 25. These are some important results we will use, right? Okay, so so now, so what we have done is we are going to choose the families of the functions defined by these, which is sin mx and cos nx, as our choice of basis functions. And the reason for that is essentially two things. First of all, they satisfy the same kind of periodicity as desired with the function, and then they also kind of form the orthogonal mutual orthogonal basis. Okay, their overlaps are 0. Okay, so that is a very useful property and it's very convenient. Okay, so that leads to a lot of simplified maths that we can do with any function. So okay, so next, so basically choosing basis functions as 1. That is, there's always a constant there, because cos nx mx for n equal to 0, that's 1, right? That's 1. And then cos x, cos 2x, cos 3x, and sin x, sin 2x, sin 3x. This forms my choice of basis functions, right? So I'm going to write down fx as simply a0. Let me write it like a0 by 2. That's a big function of a0. And then a, so if you remember, in general I can write down ak by kx. So that is my basic idea. I can decompose the function in basis basic functions. So this is what I'm going to do. An cos nx plus bn sin x. First result in last page. Satri, what the first result in last page? What is the first result? This one? You mean to say this one? Okay, so well, as I said, so this is odd function and this is even function. So odd and even multiplied will be the odd function, so therefore it will be 0. Odd function from minus a to plus a is always 0. Integral of odd function from minus a to plus a is always 0. Does that make sense, Satveer? Yes, no. This is an even function in x. Okay. So, okay, so this would be your, this is the proposed Fourier, this is called Fourier series. Fourier said that periodic function can be expressed like this. Now, you may be wondering, you are restricting yourself to very special class of function, periodic function. How useful is that? Well, first of all, there are quite a few functions, quite a few cases, okay, physical situations where you define properties, you find property to be periodic in nature. Okay? But even otherwise, when the function is not periodic, okay, so you can basically mimic a non-periodic function by periodic function by letting periodicity go to infinity. Okay? So if it's aperiodic or not periodic, that would mean that period, it never repeats itself, which would mean that period is the next time it repeats itself is after infinite value, after infinite time or infinite x, whatever the independent variable is, right? So that would mean that period tends to infinity. So in that limit of this entire analysis can be extended to include such general functions which may be aperiodic or not periodic, right? So that is so therefore it's good to first deal with such situation, and then we can look at its what can we learn when we let the period go to infinity. Okay, what is the consequence of that limiting situation? What do we obtain? Okay. All right, so this is Fourier series for the periodic function. Okay, and so it tells me that fx can be expanded like this, and these coefficients can be found out. Okay, first let's find out a0 value. What is a0 value? Well, if you integrate fx dx from minus pi to pi, what is going to happen? What is going to happen? So you do that each term by term. So what is going to happen to this integral cos nx dx from minus pi to pi? For each choice of n is going from 1 to infinity. Here n is going from n 1 to infinity. Okay. So for each choice of for any n, that means whether you choose cos x or cos 3x, yeah, they're zero, right? This will be zero. Okay. And what happens with this to sin mx dx? That will also be zero because it's going from minus pi to pi. Over entire one swing, more than a integral multiple of one swing. That will give me 0, 0 here. So only thing that is left is this one, right? That is a0 by 2 into 2 pi. Okay, so I can say, correct? Yes. Right. So that will be pi times a0. Okay. So 1 by pi integral minus pi to pi fx dx equal to 0. Okay. Now, what does that? So now there is an important thing to be remembered here, which is if you look at the behavior of these functions, these are such that they take equal amount of swing towards positive and negative sides of x, right? So meaning to say that cos mx and cos nx will have this kind of form, right? Right. So they will swing equal amount this way and this way, this way and this way, this way and this way and so on. Okay. So let's say this is 2 pi. Okay. So this I'm showing is a sine 3x. Basically. So all functions will be. So this is my fx. I'm sorry. So this would be my, let's say, any of those 5 cases. The basis functions. Okay. So this is the 0 line, right? This is my 0 line. And this function is going to swing up and down by equal. Every time it goes up, it has to go down, right? That is for sure. So therefore, net overall effect is 0. Okay. If you look at the area under the curve, it's going to be 0. Okay, because I have as much as positive area as negative area. So area under these curves are 0 because I am currently saying that these integrals are 0, right? However, if I add some constant to this function, how is that going to look like? Let's say if I add this to 1, okay, all it's going to do is it's going to raise the 0 line to 1 line, and then it's going to look like this. This would be 1 So whatever that this is sine 3x. Let's say this is sine 3x. This is sine 3x. Then this would be 1 plus sine 3x. Get this number, this length. Okay. You all agree to that? Okay. So if you add a constant, all you're going to do is you are going to take these oscillations. Okay. So any of these oscillations over here, sine or cos oscillations, you are going to raise it up by a constant value, up or down, depending on this positive or negative. But you're going to basically offset it. This is also in a signal processing. This is known as DC offset. Basically, DC offset. It's equivalent to having an AC current, AC voltage or current that goes like this, and you add onto it a DC value, some kind of DC current, and net value of the potential or the current you are going to see will look like this. Okay, so that would mean that you have applied this much of constant current, which is DC, and that's why it's called DC, sometimes referred to as DC offset. Okay, and this constitutes your DC offset, and rest of it constitutes your signal. Actually, the oscillation which represents a signal. Okay, so that's why this is essentially DC offset, which is nothing but the average value of the fx. Okay, this is average of fx. Okay, so first term, the constant term is the average of fx over minus pi to pi. Okay, you can see that it's actually it's twice of the average. Okay, fx dx. How do you define average of any quantity? Well, you integrate from a to b and divide it by b minus a, right? So if the average of f would be here fx dx from minus pi to pi divided by 2 pi. Okay, so twice of the average is a0. Okay. So that is on a0 by 2 is the average. Okay. Anyway, so that is your average value of that's related to average of fx. That's the first term. Is that all right? Okay. So that's what you have to understand with respect to for the first term. And other terms are the oscillatory parts. Okay, which would give you net. Rest of the terms would not contribute to the average value of fx. Okay, but it will tell you how the fx is varying. Okay, how there is a variation in fx. That variation in fx is captured by these series, right? This series captures the variation, and this part only gives me net offset. That is the average value. Okay, all right. So so now these quantities. First of all, I know a0. A0 can be actually obtained if you know the average value. You know the a0 value, right? How to find an and bm? Well, so you can use the formula that we discussed. Okay, about cos mx and cos nx functions, right? Or sin mx, sin nx functions of some relationship that we discussed. Using those relationships, we can see that if you do this operation, you do this calculation fx cos mx dx, okay, going from minus pi to pi, that will turn out to be well, that will turn out to be actually, if you choose m to be 0, okay, that will turn out to be a0 pi if m is equal to 0, okay, and it turn out to be am pi, okay, if m is not 0, okay. So basically, and similarly, you can look at this thing sin mx dx, that will turn out to be equal to bm into pi. Okay, so you can see that basically using these, I can write down a m equal to 1 over pi minus pi to pi fx cos mx dx. Okay, and m is equal to 1 over pi minus pi to pi fx sin mx dx. Okay, these are relating, basically telling me how to find am and bm values. Okay, those relative weights of each sinusoidal functions will be obtained by doing these operations on fx, right? So take fx, multiply with cos of mx, then take the integral. Whatever number I'm getting on right hand side will be equal to a. If you cos x here, I'll get a1. If you cos 2x here, I'll get a2 and so on. Okay. Now this should make sense because remember, if I have any vectors in three-dimensional space R and I want to find out its component along, let's say, x direction, what do? I take R dotted with E1, right? That will give me x1. Or R dotted with E2 will give me x2 and so on, or y, okay, and so on. So this is the same idea. I take fx, I want to find am, meaning that what would be its what would be the weight of the mth basis function. Okay, what do I do is I just take the dot product of fx with the mth basis function, which is cos mx dx. Okay, 1 by pi. This is my simple nothing but taking fx, dotting the fx is analogous to dotting the fx with mth basis function, which is am cos mx, right? So I'm just so fx into cos mx dx 1 by pi minus pi to pi. This is nothing but taking a dot product of f with the cosine mx basis function. And similarly here, I'm taking dot product of fx with sine mx basis function, and I'm recovering the corresponding coordinate. Right? So it's just like taking dot products, right? So this is analogous to taking dot product of the function with basis function, okay, to obtain the corresponding weight. Okay, that is an or am or bn, right? Okay, so that is how you find am and bn, right? Okay, we'll just look at example quickly and then we can stop. So one example which you might have done probably, and I'll just write down. I have a square wave. Okay, so I have a, let's say, square wave kind of arrangement. Okay. So this I'm going to choose my x equal to 0 so that I have an odd function here. This is my x equal to 0. And my function is periodic, so that looks like this. So, for example, where would this be useful to, let's say, chemical engineers? Does anyone know any example, any application where these kind of functions are used for some special purpose? Anyone knows? Or even petroleum engineers? Even petroleum engineers. Step input, right? So yeah, it's actually, well, it's a step. It's not exactly step input. Step input looks like simply this. Okay, so it's a periodic pulse, right? It's a periodic pulse. So where do you use it? Step input. Where do you use step input to do what? Reactors, clippers. I do not know about clippers. Yeah, plant control is one. Reactor analysis, exactly. Reactor resistance and RTD, exactly. That's what I was thinking. RTD, resistance time distribution in chemical is, you want to classify, if you want to characterize reactor, you give inputs which may look like this, okay, and that's so if you know the response of the function, response of the reactor to these kind of inputs, you actually know a lot about the reactors, right? And similarly, as far as I know, in petroleum engineering, you have probably something like uh, you have a drill, you have a borehole, and you want to characterize a reservoir. What you typically do is apply pressure over here and measure pressure drop across a distance, right? So that pressure that you apply here can look like either sinusoidal function or a periodic step function, something like that. And then you can look at the response at some different point And this way you can characterize a reservoir which is actually causing this kind of pressure drop between 2 points. Okay, so that is one example which I'm aware of. There may be other examples in petroleum engineering also. Okay, so anyway, so this so this is, it's good to know how to represent these functions which are periodic functions in terms of sinusoidal functions, right? Okay, I do not know what is a clipper. Clipper, Rohan, I'm not aware of clipper. What is a clipper? You may let me know about that later. Okay. Okay, so that would be the relevance of this kind of sample problem. Why we are discussing this. So now I want to decompose this in sinusoidal function, right? So what can anyone tell me quickly what will be the A0 value? Just looking at the function, can anyone tell me what's going to be the A0 value? Oh, for some reason I'm not. Okay, am I audible now? Okay, so this would be your 0 to pi. Okay, and do this. This is fairly simple and real time factor is 0. Okay, so cos, well, it's obvious. You can look at this odd function. Fx is an odd function. Cos is an even function. Odd into even from minus pi to pi, that should be 0. There's no big deal about that. So that tells me that an all the ans are 0. That means cosine part is absent in my series, and bn turns out to be simply 1 by pi. Do the same thing, minus k sine nx dx from minus pi to 0 plus k sine nx dx from 0 to pi. Okay, and that turns out to be, it has the following form. It turns out to be 4k by pi if n is odd and 0 if n is even. Okay, so what it tells me is that quite a few terms are absent in my series. First of all the cosine terms are absent because ans are 0. A0 is 0 because average is 0. Ans, all the cosine part is absent. And even among the sine part, only those sine oscillations are present where it oscillates odd number of times. There is no even oscillation present, right? So that would mean that I'm going to write this as simply I'm going to write this as fx would be equal to 4k by pi sine nx by n. Okay, where n is odd. Okay, so that is basically 4k by pi. Sorry, 4k by pi, and that would be sine x plus sine 3x by 3 plus sine 5x by 5 plus 1. Okay, okay, so this is your fx. This is going to be your fx. Okay, that's a representation of my periodic function. Now I want you to do one simple exercise. Okay, plot the right hand side, okay, with, let's say, 5 terms, 10 terms, 20 terms. Plot these. Okay, simple. You just have to plot. You can use a MATLAB. You choose k value to be something. It's up to you. Some constant you can choose k to be, and then just plot this and see what result you get. Plot in MATLAB. Okay, and see that. Okay, so I'm going to stop here, and we'll meet again tomorrow. Okay, any questions? Please submit. The others who have not submitted, I am giving grace period again until this evening. Okay, after that I will not accept. All right. Okay then, bye bye.